Hey everyone, welcome back to this video series where we solve a bunch of network challenges using Elixir. If you're new here, my name is Andrea and I'm a member of the Elixir core team. This is the 6th video of this series. If you haven't been following along, you can start from the first video, which is linked up here. Otherwise, let's get going. In this video, we'll have a lot of fun, I promise. We're going to move away from passive sockets and use active sockets for the first time. We'll also dig a bit deeper into OTP and we'll build a reliable little server using supervision trees. Okay, so we're working through Protohackers problem number 5, mob in the middle, so let's have a look at that first. The gist of this problem is to build a small proxy for the chat server that we wrote for problem number 3. The video for that is linked up here. And this proxy is supposed to look at the content of all the messages that are coming from clients and from the upstream server and detect strings to replace. The problem description calls them bogus coin addresses. The rest of the behavior is exactly the same. Protohackers itself is hosting a chat server here at chat.protohackers.com on this port. And this is going to be the server that our application will be proxying for, so the upstream server. Our proxy is simpler than the chat server that we wrote because it's not really broadcasting to connected clients or handling new user joining or leaving. The Protohackers chat upstream server is the one doing that. So that chat server on Protohackers is essentially what we wrote in the problem number 3, I think. I think it was number 3. And so our proxy is really only forwarding messages from clients to the servers and vice versa and replacing these bogus coin addresses. If you want to dig deeper into the problem description, as always, it's linked in the video description below. So take your time to go read it through so that you understand exactly what we're building. I also linked the description to the chat problem down below in case you want to have a better look at that protocol as well and to have a better understanding of what we're building. Let's start from a networking perspective. Our socket setup will be pretty simple. We'll need to have a socket for each client that connects to our server, which is an incoming connection. And each of those sockets will also have to have a corresponding outgoing connection to the upstream server on Protohackers. When a client opens an incoming connection, we open the corresponding outgoing connection to the upstream server. If either of those connections are closed by the client or by the upstream server, then we will close the other connection. Okay, so the networking should be pretty straightforward with what we know from previous videos. The OTP setup will be more interesting and challenging a bit. We will use sockets in active mode this time, so let's start with talking about that. In the previous videos, we always used gentcp.receive to receive data from a socket, but this function blocks until there is data to receive. As I mentioned at the end of the last video, blocking for long periods of time in a Gen server is a bad idea because it prevents the Gen servers from receiving system messages. Okay, so in our architecture, we will have a Gen server for each client. So let's start with that. And this Gen server will hold the socket to the incoming connection. So inside it will have, let's say, a socket. Okay. And we'll also open a socket to the Protohacker server for the outgoing connection to the upstream server. So it will have also another socket, which we'll call out sock. And basically this will point to a client, which is a person, sort of. And so a client is going to use this socket. And then we have Protohackers server and our socket that points to the Protohackers server. Perfect. When the incoming socket receives a message from a client, then it sends it to the Protohackers server. When our outgoing sockets receives a message from the Protohackers server, then it forwards it to the client. So that's our architecture. Okay, but how are we going to supervise and structure these processes? Well, these Gen servers should probably belong under a supervisor that supervises them with a strategy of 1-for-1. This should make sense since these connection processes are really independent from each other. So one going down shouldn't affect any of the others. The other choice we can make in this case is that since we don't really know how many connections will be open at any given time, we'll use a dynamic supervisor to supervise these connections, spawning a connection process under it every time we accept a new connection. So our supervision tree will look like this. We'll have a dynamic supervisor, and it will supervise a bunch of these, it will supervise a bunch of these gen servers, right? Let's call it GS, and this is also GS, and it will supervise a bunch of them dynamically. Perfect. Well, we have our connection handling architecture. However, we also need to think about how we're going to accept connections. In previous videos, we always used a single acceptor process that first called gentcp.listen to open a listen socket, and then went into what we call an accept loop by calling gentcp accept, then spawning a new process to handle the accepted connection, and 3, going back to the beginning of the loop and just keep going. We're going to do something similar for now, but we'll use a task to run the accept loop instead. This is likely a better choice in a case like this because this process is not really meant to be receiving messages and can be stuck in a constant waiting loop. So the only thing left to do is figure out how to supervise the connections and the acceptor as well. We'll expand on this later when writing the code. We'll have more details, but the idea is that we will have a top-level supervisor for our server. So this is going to supervise 2 children. One of them will be the dynamic supervisor for our connections, and the other one will be the acceptor task. Let's write acceptor task. So this will be our supervision tree. So we'll have the main supervisor over here, then the dynamic supervisor that supervises all the connections, not this one, and then we will have the main supervisor supervise also the accept task. So with this design, our server checked the reliability boxes. If a connection crashes, for example, then it doesn't affect anything else. It doesn't affect any of the other connections. If the acceptor pool crashes, then it's restarted and it doesn't really affect anything else. So we seem to be in a pretty good spot. However, scalability can be improved. So we definitely don't need it for this particular problem, but let's talk about it to have a better understanding of these OTP practices. If you think about it, as our solution has one bottleneck. You can usually spot bottlenecks by looking for singletons, which are resources for which there's only a single instance in your application. For us, it's definitely the acceptor, the task that's accepting new connections. We only have a single process that's accepting the connections, a single task. True, as soon as it accepts a new connection, then it will spawn a new process and it will be ready to accept a new connection. So it doesn't really handle the connection, it only handles accepting new connections, but it's still accepting a single connection at a time, which can become a bottleneck if you have many clients trying to connect at the same time. However, luckily, gentcp allows us to scale this up. Once you have a listen socket, which is the one returned by gentcp.listen, then you can pass this listen socket around processes, and any process can call gentcp.accept. So more importantly, multiple processes can call accept at the same time. Because of this, a better architecture from a scalability perspective would probably be to have an acceptor pool. This is a pool of processes that are ready to accept connections. So instead of having an accept task over here, we would have something like a pool supervisor. So we'll have something like, again, a dynamic supervisor or a static supervisor, it doesn't really matter. And this would have acceptor tasks, acceptor, and again, and again. So all these acceptor tasks would be accepting connections. We would open a listen socket somewhere around here so that we bind to a specific port, and then we will pass this socket down over to the pool supervisor and then to the acceptors. And that way all the acceptors can be listening and accepting new connections at the same time. So if you look around at Erlang and Elixir libraries that do these sort of things, then you'll see that practically all of them have socket acceptor pools in there. The 2 biggest libraries, which are Range, which powers the Cowboy HTTP server, and Thousand Islands, which powers the All Elixir Bandit web server, they're both doing this exact thing. They have socket acceptor pools and they're scaling up as well. They're scaling horizontally as well. In this problem, adding an acceptor pool would take our focus away from the active sockets that we'll deal with and with the rest of the OTP architecture. So I decided to not really care about scalability too much. We'll only care about reliability. But now you know what to look for and think about if you would find yourself in a case like this. So whether you believe it or not, we're ready to write some code. So let's dive into it. Okay, let's start with creating our main supervisor. So I'll just create a new file, Protohackers. man in the middle, or sorry, mob in the middle, supervisor.ex. And I'll go in here and we will create a new module, Protohackers, mob in the middle, supervisor. I will call use supervisor to create a module-based supervisor. Okay, and then I will create a start link function. It takes no options, and it will call supervisor.startLink with this module and no args. I don't really need to pass down any arguments. Then I will implement my init callback. It takes no arguments, and I will say children for now, an empty list of children, and then I'll say supervisor.startLink, and it will take supervisor.init when I return the value here, and it takes a list of children, and the strategy is going to be 1 4 1. Fantastic. So let's also add this to our application supervision tree. So we're going to say protohackers.mob in the middle.supervisor. Okay, so we're good to go. As we mentioned, there are two components to our supervisor. There's the socket acceptor, which accepts new connections, and then there's the dynamic supervisor that supervises every connection. Let's start with the socket acceptor. As I said, this is going to be a task. So I'm going to create a new file, lib protohackers acceptor.ex. Let's go with this. Okay, and let's add it to our list here, protohackers mob in the middle.acceptor, even if we haven't created it yet. And well, let's create it. So protohackers acceptor. Okay, so let's fill it in. We said this is a task, and we'll use a module-based task, which is just a task with some conventions, basically, and we call use task. We can say restart transient here. So this means that if the task is going to stop with reason other than normal or shut down, so if it doesn't stop gracefully, then it's going to be restarted, which means that if there's a crash, it's going to be restarted. If we stop it manually, then it's not going to be restarted. It's going to peacefully die, basically. So, which is good for when we're shutting down our application when we deploy, for example. So restart transient it is. We'll require logger so that we can log stuff, and then we'll define a start link function. Again, it takes no options, and what it's going to do is going to do start task.start link, and we'll call a function in this module. So let's call it run and pass no arguments. So we're going to define the run function now, and this is the thing that's going to call gentcp.listen first to bind a new socket on a port, or like a listen socket on a port. So we'll use 5006, which is the next port, and we'll pass some options. We'll pass binary so that we exchange binaries, which we use this a few times by now. Then we'll say if other let's bind to the 0000 address. Then we'll say active true. It's the first time we're going to do this, and we're going to talk about it a little bit. And then reuse other true so that we can kind of like, this is just to start it. Sometimes it gets stuck if you don't do this. So, okay, listen socket. Fantastic. And we'll say logger.info. Mob in the middle server listening on port 5006. Great. And then we'll start, we'll go into an accept loop here with the listen socket. If this returns an error and a reason, we'll raise an error so that we see this raise fail to listen on port 5006, and we'll put the reason in here. If this is so that we can, the supervisor is going to restart this essentially. If there's a problem with binding on the socket, if there's a problem with just starting the listen socket, if there's a problem such as the 5006 port is not available, for example, this might cause this process to restart quite frequently in a short amount of time. But the supervisor, then it will bubble up, right? The supervisors have a maximum number of restarts that children can do, and if they go over the number of restarts, then the parent supervisor crashes, and so that propagates. So in our case, we probably stop our application basically. Okay, so we're good to go to write the accept loop function, which is the one that is going to do the accept loop, well, from the name. And what we're going to do here, we're going to call gentcp.accept, which we've already done in previous problems. It takes the listen socket. And if it returns OK socket, then what we will do is we will call protohackers.mob in the middle connection supervisor, which we haven't written yet. We will do that in a second, and we will call start child, and we'll pass the socket. So we haven't written this module or this function yet. We'll do that in a second. But the idea is that we hand the socket off to a new process. And if then we just go back into accepting new connections. If this returns an error and a reason, what I can do now is I can probably just logger.error. Actually, let's just raise here as well. Failed to accept connection. I don't want to keep going here because if there's a problem here with accepting and the socket is closed, I don't want to just go back in this loop. I probably want to go out and let the supervisor restart this whole thing. Okay, so let's create the connection supervisor now. Let's start by creating the file. So I'm going to say Protohackers mob in the middle connection supervisor.ex. I'm going to open that file and let's fill it in. Protohackers connection supervisor. Okay, and we'll say use dynamic supervisor. As we said, we are going to go with a dynamic supervisor here, and we're going to go with a module-based one. We're going to say start link. Again, this doesn't take any options, and it calls dynamic supervisor.start link with this module with no arguments and with the name module. So the reason we're giving the supervisor a name is so that the acceptor task can find the supervisor when it needs to spawn off a new connection, right? So it's important that we can kind of find this and binding it to a name, like registering it under a name is a good way to do that here. Okay, great. And let's also define the init callback. It takes no args, as we said, and it calls just dynamic supervisor.init. The strategy is going to be 141, which is the only one supported by dynamic supervisor anyways. And we'll say max children 50, something like that also. And this is good because it's essentially just going to limit the amount of concurrent connections. We won't really worry about what happens if we reach that limit. We'll just pretend that we don't reach that, but we could probably handle that. But otherwise, this video would be very long. So let's just pretend that like we will never reach max children. But if we try, or if someone tries to do for example, a denial service attacks and just tries to connect a lot of connections to our server, it's not gonna it's gonna limit it to 50. It's not gonna burn to the ground. Perfect. Then let's also define the start child function that we used in the acceptor here. Start child that takes a socket. And what are we going to do here is define start child. It takes the socket. And then we're going to do, well, first thing, if we start the process here. So we start child, we pass the supervisor name, which is module, and then we pass the child spec. Let's define it here. The child spec for the new child is going to be Protohackers, and we'll use a module that we haven't defined yet, connection, and it's going to call the start link function, and I'll pass the socket as the init argument. So we'll define this module in a second, and here child spec, so we pass this to the dynamic supervisor to start a new child. And then the other thing that we need to do is that we will call also gentcp.controlling process on the socket, and we'll pass the new connection. And if all of this works, we just return OK and the new connection. Okay, so let's talk about this controlling process function. This function is really, really important. Every TCP socket has a single process that controls the socket. That's the controlling process. And a controlling process of a socket is the only one that can call receive on the socket, or that can receive messages from the socket if the socket is in active mode. So that's exactly what we want to do here. Also, the controlling process is the process that's linked to the socket. So if that process crashes or stops, then the socket is just closed anyways, as you don't have to close it manually. So that's exactly what we want here. So we're good to go with the supervisor. Let's move on to the connection gen server now, which we kind of called here, but we haven't really written. So let's create a new file here too. Lots of files on this video. Lib protohackers mob in the middle connection.ex. I think that's this last one that we will create. Okay, and let's fill in protohackers mob in the middle connection with one less n. Perfect. And this is going to be, as we said, at gen server. We'll also require a logger so we can debug a bunch of stuff. It will have a start link function, and it takes the socket as we called it from here, from the dynamic supervisor. We pass the socket in the child spec here. So it takes the socket and it calls gen server.start link with this module and the socket itself. And then we can define the init callback. So this takes the socket here, and then it's going to return, let's debug something. So let's say like started connection handler, and then we say something like okay, and we return the state. We will just create this struct in a second. So let's say dev struct socket. Okay, can spell socket, there you go. Okay, so we'll just store the socket in the state. So let's wire all of this up by also starting the connection supervisor in our mob in the middle supervisor thing. This might be a little bit counterintuitive, but I want the connection supervisor to be started before the acceptor. So here, here you go. Here I want to start protohackers.mob in the middle.connection supervisor first, and then I want to start protohackers.mob in the middle.acceptor. The child order in supervisors is important because it basically specifies dependencies between children. In our case, the connection supervisor can be up without the acceptor, but the other way around isn't true. The acceptor needs to have the connection supervisor available so that it can start connection processes when it accepts new connections, right? So imagine a case where the acceptor goes down, the connection supervisor can still be up. But the other way around, where if the connection supervisor goes down, then the acceptor is going to accept a new connection and it's not going to have a supervisor to spawn the connection process that is going to handle that connection. So that's why the order is important here. However, this also means that we should probably change one more thing, which is the supervisor strategy, because if we want to maintain this dependency between children across restarts, then we need to use the rest for one strategy. This will ensure that if the connection supervisor stops for any reason and we can't handle new connections, then we will stop the acceptor as well. So we'll do here rest for one. If the acceptor crashes here, it's not going to touch the connection supervisor, so we should be good. Okay, and now let's try to run this and see if it works. So I'm going to do mix run no halt. And it's not working, and I had to pause the video and figure out why. And it's because I put the acceptor also in the main supervisor of our application. It doesn't belong in here. It only belongs in the supervisor. So if you saw that, sorry. So, okay, let's try to connect to our server and see what happens. Let's start it. First of all, no halt. And okay, this is running, and let's use telnet, which we used for our chat server, I think, to try this out. I'm going to say telnet localhost 5006. And I see that there's a debug log saying start a connection handler. Now I say hello. And I see that the Protohackers connection received unexpected message in handle info TCP and then the string hello. So we have a hint of what to do from the error message that we just saw in the logs. But to understand it, let's finally talk about active sockets. When a TCP socket is started with active true, like we did here in our example, then the data coming from the socket is sent to the controlling process, which we talked about, as Erlang messages. So there are three types of messages: one for data coming to the socket, one for socket errors, and one to signal that the socket has been closed. The packet option works with active sockets too. So for example, if we use packet line, then messages will be sent to the controlling process only once there's a full line in the buffer for the socket, same as GenTCP receive. One more thing, Each message contains the socket itself so that we can match it back to the socket that's receiving it. This is useful if the controlling process is the controlling process for other sockets as well, not just for that particular socket. So let's get started by modifying our connection gen server. Actually, let's get started by adding packet line here because we're going to need that. And then let's modify our connection gen server. So in our init callback, we can keep doing what we're doing now. So we just debug that we have a connection and then we store it in the state. And we'll define also a handle info callback. So this is called every time there's a message coming to the gen server. So this is going to take a message and a state. So let's define a bunch of clauses for this. So we will, to make sure that we're receiving messages from the right socket, we'll always match on the socket that we have in the state. And so for now, we'll only debug the data that we received. So let's start with a clause for the messages that contain data, as I mentioned. So we're going to say the shape is this. There's a TCP item, there's the socket, and there's the data. And I'll match this against our state where the socket is the same. So socket. And this equals to state so that we can return it. And for now, we'll just say logger debug received data, inspect data. Okay, and we'll just return the state unchanged. And then we'll define two clauses to handle errors and other conditions as well. So we'll say handle info. Error messages look like TCP error socket reason. And I'll do the same where I match on the socket in the state. And I'm going to say here logger.error received TCP error inspect reason. Great. And in this case, I don't need I'll also return. I'll actually stop in this case. I'll stop with normal reason because anyways, there's no point, like we will not restart this. Our gen servers are not going to be restarted by our dynamic supervisor. And that's what we want, because once the connection has been broken, there's no point in restarting the same connection. We'll have to wait for the client to connect back to us. So it's perfectly fine to stop with a normal state, with a normal reason, so that nothing gets logged except for our log, which says that there was an error. So we know that the client disconnected abruptly because of an error. And then we also have TCP closed messages, which should look like this: TCP closed, and there's only the socket here. And then we'll do module socket. And in this case, we'll just logger debug TCP connection closed. Great. And we will also stop with normal reason, like here, nothing bad happened. We have a debug log, but nothing bad happened. Let's test this out again. I will shut down my server. I will connect again with telnet. I'll say hello, and I'll see that I have received data. Hello, world. And I see that I have received data world. So great, it seems to be working. Nothing happens to the client really, like we don't get anything back or anything like that, but we can see that our server received the data. So that's really good. Before moving on to actual proxying, I want to mention one important thing, which is that the active option doesn't support just true and false as its values. There are more values, and the most important one, in my opinion, is the atom once. If we set active to once, it means that the controlling process will receive a single message from the socket, and then the socket will go into passive mode automatically. The controlling process will have to set the socket back to active mode or to active once using a function called inet.setOpts. And this is really fantastic for back pressure. So if active is true and our server is slow at processing messages and handling messages, its message queue could just get filled up with these socket messages if we were not processing them in time, basically. With active once, we guarantee that messages are delivered to the server only when the server is ready to handle them, because we will get a message, handle it, and then set the socket back to active mode. So it's a really good choice here for back pressure. So let's do a little bit of surgery to change our code to use active once. The first thing we're going to change the acceptor here where we say active true. I'm going to say active once. Perfect. And then after doing this, we make sure that the socket is back in active mode after receiving a message. So in our connection, when we receive some data here, we debug it, and then we say inet.setOpts socket, and we say active once. So we change the active back to once instead of being passive now. So if we test with telnet now, we are going to see that it does exactly the same thing. So just to make sure that we didn't break anything, I'm just going to say hello world, and we see that we get both the data packets. So we're good to go. So one thing to mention about these active ones is that we are setting active ones after kind of handling the data, which is for now is just debugging. One small note is that this is not really the most efficient way of doing things, because what we could do is we essentially just switch these up. If we switch this up, we're already taking advantage of concurrency a little bit better, because we are going to set active ones before processing the data, which means that while we're processing the data, the socket has time to like construct the data from the buffer and send it to our process. And essentially, as soon as we finish processing the data, if there is additional data, then we will likely have it already in the message mailbox of this process, and we'll already be ready to process it. This is a tiny optimization, but it's for free, so why not do it? So let's... Okay, so we're ready to implement the proxying part. As I said, every time that we have an incoming connection, we'll open a corresponding outgoing connection to the Protohackers chat server, to the upstream server. Before doing this, let's just rename socket in our connection gen server here to incoming socket so that we can distinguish them. I can start actually all the way from here, and I'm just gonna multiple cursors, incoming socket. All of these. Okay, I'll just literally try to run it again to make sure that, okay, it's not blowing up. Perfect. And now we should start the connection to Protohackers in our init callback, so to the upstream server, right when the server is starting. After all, if we can't really connect to the chat server, if we can't connect to the upstream server, there is no point in starting our connection either. So it makes sense to do it in our init callback. Here I'm going to say outgoing socket. Perfect, so I'll add it to the state, and then I will change the init callback to, instead of logging here, I'm going to say case gen tcp.connect. I'm going to pass a char list to chat.protohackers.com, and the port is 16963. I have it written here, and I'm going to say binary and active once, so I can say the same thing. And then I say do. Okay, and if this returns okay and an outgoing socket, then I can move this over, say started a connection handler, I connected successfully, and I can say outgoing socket is equals to outgoing socket. So I store it in the state as well. If there's an error and a reason, then what I can do is I can logger.error failed to connect to the upstream server, and I'm gonna inspect the reason. And then I'm going to stop with that reason, because it doesn't make sense to continue with this connection. If we can't connect to the upstream server, there's no point in handling that. We have nothing to do for this client. Great. So now let's handle incoming and outgoing messages. If we receive a message from the client, we should send it over to the Protohackers server. So if we get a message here from the incoming socket, and it matches our incoming socket, so you see now why it's important to match on the socket here, because the message is going to look exactly the same for the outgoing socket, except that the socket is going to be different. So matching here is really important. And if we get a message from the client, what we can do is we'll set active ones for the reasons I mentioned earlier. And then I'm going to say gen tcp.send state.outgoing socket and the data. So I'm just literally going to forward the data to the upstream server. Okay, if we receive a message from the outgoing socket, which is the upstream server, then we should send it to the incoming socket. So I'm just gonna copy this one, and I'm gonna change this to outgoing socket, and I'm gonna send the message to incoming socket instead. So proxying the other way around. So for now, we're just proxying messages. I set active ones again, so that makes sense. And the problem description says that we also should close either socket if the other socket is closed. So let's implement just that. The nice thing is that gentcp.close has no effect on a closed socket. So, and we will ignore its results. So we can just close both sockets in either case. So here, if we have a TCP error, will not really match on the specific incoming socket. What I'm going to do is I'm going to delete these. I'm going to do some surgery here. And I'm going to say when socket in state.incoming socket, state.outgoing socket. So I still make sure that the message is from a socket that we know, but it doesn't matter from which one it is, because in both cases, I'm going to say gen tcp.close state.incoming socket, and then gen tcp.close state.outgoing socket. So in both cases, I'm going to just close both of the sockets and then return. It doesn't really matter. I could just let the process die, but I mean, we have, because the both sockets have this process as the controlling process, but it's nice to shut things down nicely. So I'm going to do this here. And then if I get a TCP closed, I can essentially do exactly the same thing. So I'm going to just replace this with this, but this is going to be TCP closed, and there's going to be no reason. And when the socket is in the incoming sockets or the outgoing socket, and I'm going to do exactly this thing here as well. Perfect. So last but not least, let's rewrite those bogus coin addresses. So this should all work, right? But let's rewrite the bogus coin addresses. And this is a pretty straightforward part of the problem, because it's just mangling data, basically. A bogus coin address is the problem description says that it's a string that starts with 7. I have my notes. It's between 26 and 35 alphanumeric characters, yes, and it's preceded by a space or by the start of the message, and it's followed by a space or the end of the message. You might have noticed that I elegantly glossed over testing completely in this problem, because I wanted to have an easier life and I wanted to just go through all this interesting stuff about active sockets and so on. However, I think it's beneficial to actually test this little part, because it'd be nice to test small edge cases in processing these messages and rewriting these addresses. Okay, so I'm going to say create a file, Protohackers, mob in the middle, bogus coin.ex. And in here, I'm going to just write my little module, protohackers dot mob the middle bogus coin. Okay, and I'll say that the Tony's address, and this should come from the problem description. So I have copied it over from my notes, and then I will write my function, which is rewrite addresses. Takes a string. When is the binary string? So we will write a regex here to replace. I'm not a fan of regexes. I think I mentioned this in previous videos, but it just makes this, I would usually do manual parsing, but we're trying to be faster here so we can focus on the networking part. So I'll just write a regex here because it works. So we said that a bogus coin address starts at either the start of the string or with a space, basically. And then we match the address, and there is a 7. And then there is alpha numeric here, but we have 26 to 35 of them, so 25 to 34, including the 7 that we started with. And this is the bogus coin address. And here I also want to include a backslash capital K, which is look behind, so that the string, the regex will match if there is this before, but we don't consider it as part of the match, so we don't replace it essentially, which is what we're going to do. And then here I have what we have after the string, which is either a not alphanumeric character here, or so it's either not an alphanumeric character or a space or the end of the string, which is a $sign. And I want to do the same thing, which is a look behind, look ahead here, I think. That was the look behind, but essentially I don't want to consider this as part of the match. I just want to like make sure that it's after the bogus coin address, but I don't want to rewrite it. And then with this regex, I can use regex.replace, and I can say regex string, and I replace it with Tony's address. Okay, let's just add some tests for this. So I say make file test / protohackers mob in the middle bogus coin test.dxs. Great, and I start this with def module protohackers mob in the middle bogus coin test. Perfect. Again, use xunit.case and saying true, all usual stuff. I'll alias protohackers.mob in the middle bogus coin. Perfect. I will say here also Tony's address, and I will copy it over here so that we have, I like to do this to duplicate the value so that if we change it in tests or in the code, we will notice. And then I will go in my notes and I will actually take a bunch of sample addresses that were included in the problem description here. So I will just copy and paste them here. Perfect. So these are from the problem descriptions that we can write some tests based on those basically. And then we can say test. Let's actually put this in a describe block. So rewrite addresses. We're almost done with this. And we say it doesn't do anything if there are no addresses. And here I can just test that assert bogus coin dot rewrite addresses. If I try to rewrite hello is equals to hello. Let's see if I test this, if it starts by working. Yeah, we're not using this stuff, but it's fine. Okay, so after this test, what I'm gonna do is I'm gonna just copy a bunch more tests from my notes here, and I will paste them over here so that we are not gonna lose too much time writing tests. The idea with this is that I'm just gonna show you, the idea is that we're gonna test that this rewrite function ignores addresses that are too long. So it doesn't rewrite these because it's over the limit of characters. Ignores suspicious addresses, which they look like it, but then continue with something else. Then it can handle multiple addresses. So if we join all the sample addresses, it rewrites all of them to this address. And then it just rewrites all the addresses also by adding a string after, which is left the same, adding a string before, which is left the same, and putting it in the middle. Okay, and with all these tests, I realized that also I think I got my regex wrong. Yeah, this needs a space here, and I will run the tests again, and all the tests pass. So it works. Cool. Now we need to actually rewrite every packet that we're getting with our new function. So here, when we get data from not here, sorry, here. When we get data from either the upstream server or the client, essentially, what we're going to do is we're going to say data equals protohackers dot mob in the middle dot bogus coin dot rewrite addresses, and I'm going to pass the data. So I'm just going to like take the whole data, rewrite all the addresses in there, and just forward it like I was doing before. Okay, so the last thing to do, as usual, is to open our ports on fly.io. And we'll open port 5006. I'll change this to TCP. Perfect. I will deploy and I will see you here as soon as it finishes deploying. Okay, it finished deploying. So let's head over to Protohackers and see if this is working. So I have the same address. I'm here in the problem description. I have the same address as last time. Didn't change the IP. I'll just update the port number and I'm going to run the checks. We'll see this is going to try to connect and we're going to see hopefully a few tests passing. So we see that like a bunch of people connected to our room and it says pass. So this is going to be a little bit longer to run all the tests. So I'll see you back as soon as Protohackers is done. Okay, so checks passed. Great success. I really love today's problem. It allowed me to highlight a lot about OTP architecture as well as TCP. If you have any feedback or questions, please feel free to leave a comment down below or find out how to reach out to me using my website, which is linked in the description. Well, otherwise, thank you so much for joining me and I hope to see you on the next one.